So, I want to talk today about the mechanics of Ruby, thinking in terms of Ruby is a software machine. What does that machine look like? How does it work? So, we're going to shave some yaks, digging into the layers below our Ruby programs. How does Ruby work? How does it work with the operating system kernel? And how does it work with the actual computers that are called Intel or ARM that those are executing on? But first, a story. So once upon a time, there was a guy named Mats, and Mats was nice. And every day, Mats would write lists, small talk, in Perl, but he wrote it using C. Until one day, he sat down and wrote an interpreter so that he could write small talk, Lisp, and Perl, and he called that interpreter in the language he had created Ruby. And every day, more and more people used Ruby to write small talk, Lisp, and Perl. And then one day, someone started using Ruby to write web applications, and that ended up being a really big deal. Finally, many years passed, and some people figured out that writing programs in Ruby is really great, but it involves trade-offs, and that sometimes those Ruby programs aren't as fast as they would be as if they were written in C or Java. And then from that day on, everyone was cheerful and knew how to make engineering trade-offs to optimize their happiness and make trade-offs between happiness and performance and all sorts of ilities. Yay, story. So I have a bone to pick with people who tweet about Ruby. People who tweet about Ruby are often condescendingly talking about shortcomings that they perceive in Ruby, design trade-offs that Ruby has made that they don't necessarily like. So they'll say things, and so if you strip off the condescension, what they're really getting at is that Ruby isn't concurrent, or that the GC is slow, or that Rails is too much code, too big, or that sometimes the Ruby community makes naive design decisions. And in isolation, all of these are true and worth thinking about and fixing in the long run. But what the other thing they're griping about is that design decisions and trade-offs have been made that don't work for them personally. And that's just life. If someone came up to you and be like, hey, you didn't make me a peanut butter and jelly sandwich, you wouldn't be like, go away. Well, you would be like, go away, because you don't have to make everyone a peanut butter and jelly sandwich. If they want a peanut butter and jelly sandwich, they should make themselves one. And so a lot of these criticisms, they're true, and we should figure out how to fix them going forward, but they're not necessarily like, oh, well, you should stop using Ruby because it's terrible. So what I want to get into in this talk is like, what if we were scientists and we started looking at these design trade-offs in Ruby and figuring out why they're there, why they got there, how they got there in the first place, and what we can do about them going forward, and how we can mitigate them in our code in the present. We would peel back the layers of our systems and know about the design decisions and trade-offs that were made and how to work with those when we use Ruby. And then if we were scientists, we would probably want to be fun scientists and not boring scientists. We would want to have some whimsy and delight so that we're not all just crankily complaining about GCs and threads, but having fun with saying, oh, hey, I understand that, Ruby makes these trade-offs, but today I didn't have to type malloc at all, so that was cool. So we would make use of our knowledge of how Ruby works on top of usually Unix and how it works with computers so we can optimize for happiness. So we're going to peel back the layers and do some real talk. I want to shout out to the guys who run the Real Talk podcast. These guys dig deep into kernels and compilers and assembly and bugs, and that's a really cool way to think about programming computers. So here's a weird hypothesis. Ruby is a really strange way to write C programs. If you were to pair with me, if you were to shave some yaks with me, I would probably mention this at some point. And here's what I'm trying, and let me try and prove this, not prove this hypothesis, but here's what I'm trying to say. This simple little program prints out the Beatles. It's not necessarily idiomatic Ruby, but it's 5 lines of really simple Ruby. And that's the same as this C program, which is like 4 times longer and actually executes a little slower than the Ruby code. So there's one assumption blown apart. C is always faster than Ruby. Well, you can write Ruby in any language, including C. And then that Ruby, or that C code might be slow. So here's how we ugly up that Ruby. This Ruby basically maps to this C program. So we create a Ruby module, and then we define a singleton method on it, and we create a new fixed size array, we throw some beetles in there, and then we have a for loop over it, and we print out the beetles. These are all the same constructs that C extension uses. The for loop is going to be a little higher level abstraction-wise than in the C extension, because there's no way to write just like a native for loop in Ruby. So here's that C extension taken apart. So the first thing you do when you're writing a C extension, if you've never done it before, is you include the Ruby C API by including ruby.h. That gives you all the functions that make the insides of C extensions go. And then we're going to pre-declare 2 variables. We're going to give ourselves a variable to put our beetles module in and assign it nil. So that's just your regular old Ruby nil, except in C you say Q nil. And we pre-declare a C function that we're going to use to implement that print beetles function. And you see these value guides all over the place. What that means in a Ruby C extension is, here's a Ruby object. What it actually expands to in C code is some crazy pointers and unions that could be a string or an array or just a plain old Ruby object or even something more low level. But when you're programming a C extension, all you need to know is a value is a Ruby object. And then this init beetles function gets called whenever the extension is loaded into the Ruby interpreter. And this is where you set up all your objects that you're exposing to your Ruby programs from C. So just like over here, we're going to call module.new, except that's RB defined module in the C extension. So we create our beetles module, and then we're going to attach a singleton method, just like we did here. It's going to be called print. We're telling the C extension to use this print beetles function we're going to declare in a second, and that it takes 0 arguments that aren't the self object pointer. So now we're really writing C extensions. We're into it now. This is going to be our singleton method. It takes the self object, which is the beetles module, and it's going to return some Ruby object. So in the body, we pre-declare 5 Ruby objects: beetles, name, puts, kernel, and args. And then we have a loop counter we'll call I. So this first construct right here is how you create a new fixed-sized Ruby array in a C extension. So you call Ruby array new 3. There's like 3 or 4 different variants on Ruby array new in C extensions. And then we use Ruby string new 2, which is just like a literal string in Ruby, to create our beetles. And then the rest of that function, we use open classes in Ruby to get ourselves a handle on the kernel module, because we want to call puts on it. RB intern is the same way of basically the same as creating yourself a symbol in Ruby code. So now we have the kernel module, and we have the symbol for puts, and we can use that to send a method. So we're going to loop over our beetles with this array length int macro that's going to expand to a whole bunch of C code that basically takes a Ruby array and gives you the number of items in it as a C integer. And then we're going to use RB array entry is just like square brackets on an array. So this is like beetles sub I. And then just a quirk of the C extension API is that you have to, when you call send on a method, you have to, or on a class, you have to wrap all the arguments in an array. So we take something out of the array, we put it in its own array, and then we can use that. RB apply is basically like calling send on an object. So RB apply, kernel puts args, says kernel.send puts args. And that prints out all our beetles. And that's how you turn a little bit of Ruby into a lot of C that's a little slower than actual Ruby. So what's conspicuously missing here? There's no calls to malloc or free. We're not calling into any C libraries yet. We're not calling things like fopen or printf. There's no direct system calls. We never call fork or write or anything. And there's no amazing performance. But if we squint at this, or if we have too many beers, then we can see a Ruby program kind of peeking out, especially the one where I uglied up the Ruby and was using the lower level APIs for defining modules and defining methods and whatnot. That C program was pretty easy to understand if you know Ruby at that lower level kind of meta programming state. And what we have here is a nice C API. If you've not done much C programming outside of, say, college, like myself, then this isn't too intimidating. I was able to get this level of C extension mastery, quote unquote, over the course of a weekend. And sometimes I had like weird C seg faults, but then I was like, okay, I did something wrong, I should try something else. So that's what I mean when I say Ruby is just a funny way of writing C programs. And basically everything we do with computers is a funny way of writing C programs. Whether we're writing Ruby or Java or Clojure or PHP or whatever, if you squint, you can look through the layers of abstraction and say, okay, when I have module foo in my Ruby program, what is that doing? Well, in the C extension layer, it's calling RB define module, and then it's attaching methods to it. And that's not something you need to think about like all the time when you're programming Ruby, but it's a useful lens to look things through. So, a digression. I love to digress. Rails is big. This is another Ruby complaint. Is that okay? Here's a lens to look at that through. What are different kinds of programming? Here's a procedural program. It doesn't have any functions or data abstraction. It's just doing stuff to stuff. And it's vaguely fizz-buzzy. Here's an object-oriented fizz-buzzy thing. It's using messages to invoke behavior on encapsulated objects that contain data. You can take that and convert it into something functional-esque, where you pull behaviors off of some object and then pass that behavior onto another message. You could take some of that boilerplate out and turn it into a little DSL. So now we're not thinking about files anymore. We're just thinking about when should we write out our fizz-buzz things. So we got past DSLs. What's this? Is this object-oriented programming? Is this language DSL-oriented programming? This is even further removing the boilerplate. We've got some class that has all of the logic abstracted into it. All the boilerplate is living off in some framework somewhere. And we just write some logic, or distill some ideas, and then call some magic method, and all the things happen. So what is this? I moved that this object has superhero powers. It's just like when Bruce Wayne puts on his Batman suit, or when Tony Stark puts on his Iron Man suit, all of a sudden, they can do extraordinary things. They're normal dudes. Their only actual power that most of us don't have is that they're rich. But when they put on that suit, they can save the world. And the same thing applies to like active record base or action controller base, a lot of the Rails framework. You have a normal object and it inherits from some superclass, and all of a sudden it can do amazing things. It can save the world. So active record base is an Iron Man of object-oriented programming. The thing about superheroes is that they always have some lame weakness. Whether it's like kryptonite or Tony Stark being a raving egomaniac, there's always something that's going to trip them up. Otherwise, their stories wouldn't be interesting. And when, for instance, Iron Man gets in trouble, things get really messy. And it's not like one toddler left unsupervised for 5 minutes messy. It's like, oh, I totally destroyed a city block and you should see the next block. It's pretty bad too. And the same thing goes for active record. When you get in trouble with active record, it can get really weird really quickly. And so Iron Man is really good at saving the world in 90 minutes, and active record is really good at putting an application together and teasing out an idea in a few weeks. But on the long run, Iron Man is a pain in, for instance, Nick Fury's neck. And he'd rather have a flying aircraft carrier full of normal people with normal egos that he can just say, oh, hey, we need to save the world. Go do this thing in my awesome flying aircraft carrier. And on the long run, you'd rather have a few dozen objects with a few methods rather than having a whole bunch of active record model objects. So you don't need radical approaches to make your Rails apps manageable. And it's not so bad that Rails is huge as long as you're using it in moderation. You just need to use, I've found that I can use procedural, object-oriented programming, and functional programming when they're appropriate. Sorry, some of this got cut off here. When they're appropriate, and that helps me take a program that is starting to get Rails unwieldy and then start applying just normal software development, functional programming, object-oriented programming, structured programming practices to keep it reasonable. And then I don't have a lot of the program, and then that keeps me away from a lot of the trouble that people like to stereotype Rails as having when they talk about Ruby. So I hope that is useful to you. Perftools, perftools, perftools. Perftools is your new bicycle. So your application has bottlenecks. Statistically, I'm almost certain of this. You spend a lot of time in GC because Ruby's GC isn't that great, and because the way people write Ruby generates a lot of garbage. You probably want to know what your application is really doing, either because you just introduced a gem that does weird things and you wonder why that happened, or because someone just handed you an application and asked you to change it, and it's 30,000 lines of Rails code, and you're not exactly sure what the person who wrote it was doing. And you probably, if you're like me, like pretty cyclic graphs. Perftools is a silver bullet for all of those things. It's wonderful. So here's a laughable database. It generates random people-esque things and writes them to dev null. I will be selling support contracts for this database after this talk. I want to peek inside. I want to know what my laughable database looks like as it's running, and I want to know what its bottlenecks are and what its performance is like. So to use perftools, you gem install perftools.rb. Perftools is by Aman Gupta. He is amazing, awesome. Just follow the things he does. He does amazing things to Ruby. There's two things that I find really useful to do with perftools. If you run it with the environment CPU profile methods set, then you can get it will basically measure all of the method calls in your Ruby program, and then you can see who's calling what and how often. The default is that it just wakes up 1,000 times a second, sees what Ruby method is executing, and records that. And if your program runs for more than a few seconds, then you've got a few thousand data points, and you can start figuring out what your bottlenecks are and what your program is really doing. Once you've generated data by calling perftool CPU profiler.start and doing some stuff inside of a block, you can use the pprof.rb tool to generate a PDF. It can also generate GIFs and SVGs, but PDFs are wonderful because you can just zoom right into them. They don't lose resolution, and you can kind of move around in your program as though it was a map. So this is the PDF output when I run my laughable benchmark on my laughable database. And from here you can see grossly like where the time is spent. You can see it's spending about a quarter of the time writing things out to dev null, It's spending a lot of time generating a string. So that's probably something I would look into because I would hope that would be faster. And it's spending about 1/5 of its time in GC. This is what the method call graph output looks like. It's the same sort of thing. But here you can see that it's calling rand a lot more than I would think for the code that I had before. But if I had just inherited this program, this is a great way to start and figure out what is this code doing, because you can see the entry point at the top, you can see where faker is being called, and that's calling a bunch of stuff. It's a fantastic discovery tool. More practically speaking, you can use perf tools inside of rack and Rails applications. You throw this thing into your gem file, you add some middleware. Like I said, I like to use the PDF output by default. And then you go to your whatever URL in your app, you say profile equals true, and you use time. This is the number of times to run that action to get a reasonable benchmark number. So 10 times is probably going to be very sufficient, and maybe you won't time out your browser. And this is what a typical Rails app looks like. I work on an app called Sifter. It's an issue tracker as a side project. I just loaded up the slowest action, or one of the most frequently called actions, with perf tools, and looked at the output. So here you can see, I actually already pointed this, you can see all the rack middleware. So if you've ever read Aaron Patterson talking about rack, he's pointed out that this long, nasty call stack is problematic. All of that stuff has to hang out in memory. It's part of what makes your Rails stack traces really long and tedious these days. So there's that. Here you can see a little bit of action view rendering going on, action controller and all of its base classes and whatnot. And then, boom, a bottleneck appears. So what's going on here, and how can I read this? So the way that perf tools is set up, you always have callers above callees. So Haml block as Haml is calling kernel eval 590 times. 590 times when the perf tools sampler woke up, that's what was executing. So there's total calls, and then there's the method name for each block. So kernel eval was active in 47% of the samples, or 590, and it was actually in eval, executing eval code 37.8% of the time. So I dug in to my app, and it's weird that Haml's getting called this much because Sifter doesn't use Haml at all. And that's problematic, and possibly a waste of time. And what it turns out, yeah, I thought this was weird, and I was like, okay. So I looked at my gem file, .lock, to see who depends on Haml. And it turns out it's Mailcatcher. And Mailcatcher, you don't actually run within your application, you run it kind of to the side of the application. But through the wonders of dependency management, it was in our development group in the gem file that was causing it to get loaded by Rails. And so every time Rails was looking at a template in action view, which Sifter has a lot of templates, and each view ends up calling a whole bunch of templates. Every time it was saying, it was deferring to Haml and say, Haml, do you want to do anything with this? And then Haml would be like, nope. So it was a total waste of time. So I removed it from the gem file, and now everything is uniformly slow. I'm spending about 26% of my time in GC, which I could maybe dig into that and try and tune the garbage collector, but like I said, the way people write Ruby is something that is a way that generally creates a lot of garbage, and I'm still digging into ways to write Ruby without so much garbage. And it ends up spending about 50% of its time buffering ERB templates. It turns out modern web applications are all about taking strings in, twiddling them, and pooping strings back out. So you're going to spend a lot of time in ERB. So in about 45 minutes of exploration with perftools, I found a really weird thing that my application was doing. I went from about a second to render this issues listing and was spending a half a second in action view down to about a half a second to a 3/4 of a second, only a 1/4 second in views. So everyone who works on Sifter is going to be happier in development mode, and all I had to do was move some stuff around in the gem file. I didn't have to really write any code. So that was pretty awesome. And it was all from using a tool, perftools, to peel back the layers, figure out what's going on inside my application, and stop doing things that the machine doesn't like it when I do them repeatedly. So it's measure, experiment, rinse, repeat, and then you're doing science. It's awesome. And then you're a scientist. And we all want to be prankster scientists, I hope. So, more directions. What is Ruby? Previously, I said that Ruby is a really strange way to write code in C. And that's because, and right now, and part of that is because MRI is written in C and because of its design. When you're writing Ruby, you're basically calling C things in a really strange way. I think a lot of the tension about Ruby and why it isn't so good at concurrency, why the GC is slow, and its release patterns is because MRI as a piece of software is misunderstood, and it can't be all things to all people. So the first thing that Ruby is a scripting language. It scripts text and working with text. That's the Perl heritage. It scripts working with C libraries because that's a useful thing to do. And it scripts object interactions. So it's easy to do small talk style object-oriented programming, and it's easy to jump down a level and automate doing things with objects, so doing metaprogramming. The flip side is the MRI is not Hotspot. It's not the JVM. It's not V8. It's not Node. And it's not Erlang. So it doesn't have the best minds on the planet of VMs working on it. So it's not going to be as fast as Hotspot or V8. It doesn't have the best minds about concurrency and reliability working on it. So it's not Erlang. So that's just a fact of life. It's a trade-off. It's more pleasant to use than Hotspot or Erlang, but it's not as fast, and it probably won't ever be as fast. Ruby's core team has different ambitions than a lot of us in America doing startups, working at Rails shops. Their goals are different, and that's part of why MRI is never going to be Hotspot or V8. They're prioritizing developer happiness over high performance. They're prioritizing having a global variable lock so you can only run Ruby in one thread over having to have a bunch of application level mutexes and locks and whatnot in your code. And they know processes as well. They know how to work with them, what works and what doesn't, the shortcomings. And so MRI for the foreseeable future will probably be process-centric instead of thread-centric. Standardization is also something that we're over on this side of the Pacific not so enthusiastic about. When the standardization of Ruby was proposed and announced, a lot of people I know thought it was maybe not so useful or maybe even not so great because standardization, who needs it? If I want to use Ruby, I can just start using Ruby. My understanding of this, and please correct me if I'm wrong after the talk, the Japanese tech culture is not as easy to just start using something as it is here. And so having a standardized body say, hey, Ruby is great, means more people in the Ruby core community can start using Ruby for their day-to-day jobs, and that's pretty awesome for them. The third thing is that Ruby does not use Linux or semantic versioning conventions. This seems to confuse a lot of people. Several of my friends said, hey, why didn't Ruby 2.0 do big drastic things, get rid of legacy cruft? The basic reason is that Ruby doesn't have major versions. You basically multiply the first two numbers by 10, and then you'll get a sort of semantic versioning number. So Ruby used to kind of do the even, odd, stable, unstable series thing, but doesn't do that anymore. And semantic versioning was not even invented when Ruby started. So if you look at a Ruby version number, say 1.9.3 P327, if you want to understand what that is in semantic versioning, you get version 19.3.327. The reason I understand that they do it this way is because of how FTP servers sort files. And that's an important thing for them, so that's how it's done. So just knowing that they're working in a different way is useful to understand like why there's still like the SOAP library in the Ruby standard library, is because they're a little more conservative about pulling things out, and because, and I lost my train of thought. So it's more because they're more conservative, and because they're not going to break things as readily as we would in our fast-moving startup American business cycle. So the way to work around this is that MRI isn't Ruby. MRI is just is not the Ruby. It's the Ruby to a lot of people, but it doesn't need to be. The more we can adopt JRuby and Rubinius, the more Ruby is just a language, and MRI is another implementation of it, and it's just the one that gets the new language features first. JRuby and Rubinius are actively trying to make really high, trying to make VMs that are comparable to Hotspot or V8 or Erlang's. And the more that we can get on board with JRuby and Rubinius, the design tension between MRI and Western Ruby becomes a minor detail. They can, they can move in their sort of more conservative way. We can push ahead and work through the breakage. So, I'm not sure how I'm doing for time. I have a wrap up, and then there's another section, a bonus section, if I have time. MRI is knowable. We can peel back the layers and understand the mechanism. We can understand how the machine works. We can also peel back the culture and understand how Ruby core works, why they do things the way they do. We can spot bottlenecks and identify design trade-offs. And then we can decide how to mitigate those things and improve them in the future, or we can figure out how to live with them in the short term before we can fix them. So, you have homework. I apologize. You need to go read things. Go read code especially. But read Jesse Stormer's books on Unix processes and threads and on TCP sockets. They're like 100 pages each. So just pick one and read it, and if you like it, keep going. He's a great writer. A few of them come with like screencasts and cheat sheets. I use the cheat sheets one for the sockets book all the time. If you want to understand how Ruby works internally, how YARV works, how hashes work, how regular expressions work, then you should check out Pat Shaughnessy's Ruby Under a Microscope book. He takes it all apart, makes it all very obvious. Once you've read those things, once you've dug into some source code, go off and write your own echo server, write your own memcached client or server, an HTTP client or server, a tiny little laughable key value database, a threaded queue worker. I've been digging into that stuff over the past year, and like all parts of my programming abilities have leveled up. I'm better at web programming, but I'm also, I feel like I could talk about these things with people who really know about them. I could be conversant, and that helps me program better since I know how more of the stack works. And finally, most important, poke the insides of your project. Poke inside Rails. Poke inside the gem you're using. Don't be content with just saying, oh, this is the Ruby interpreter, so it's too low level for me. Or I don't know how this gem works, so it's magic. There's no magical things. There's only things you don't understand yet. So poke the insides of your projects, make them faster, or figure out why they behave in weird ways and how you can work through that. So hold your wild applause. I'm going to keep going until they kick me out or until Brian kicks me off the stage. MRI is a virtual machine, called YARV, and it runs on a kernel that's called Darwin, and it runs on a computer that we call x86. So this is all about digging in, like what is actually going on when I run a Ruby program. You shall know Ruby by its runtime behavior. So, like I said, garbage is expensive. Here's a stupid little benchmark that measures just basic integer arithmetic with a junk string in there, and then allocating an array. And the basic arithmetic is the fastest. It's not horribly fast. This, on a 2 gigahertz machine, doing 1 million adds in 600ths of a second is pretty not that great. Should be able to do 2 billion adds. Adding the string in there is only marginally slower, but doing the arrays is really slow. So yeah, garbage collection, creating stuff is expensive. It's not cheap. If you can not do something like this on the inside of a loop, don't do it. But let's drill down into this program. We can take it apart with a really neat tool called dtrace that's available on things that aren't Linux or Windows. So you can't use it on your production servers, sorry. But you can probably use it on your laptop. It's available on OS X, FreeBSD, because I know all of you are running FreeBSD on your laptops. So what it lets you do is, as your program is running with no overhead, poke the insides of it and see what it's doing. So you write these little probes in a language called D. So basically you just go online and copy this from someone else. But we can poke the insides and see what is my object, when is object create and object free being called inside the Ruby interpreter. These are Ruby specific hooks. And then this one is a system global hook for when is malloc called. And then if you've ever done set or awk scripting, this might look similar. Or you can do that stuff in Ruby, which is awesome, that I didn't have to learn set or awk one day. So this is going to print out the summary of all those collections. So I run dtrace on that add benchmark from before, and I took out everything but I took out the garbagey one. Or no, wait, maybe I didn't. This is the one with everything. And you can see malloc is called millions of times. So that's probably not cheap. If I take out that junk array, then malloc is only called 35,000 times, which is a vast improvement, and that's why the program is faster. The one with the junk string is about the same number of mallocs, and it turns out object create is constant across all of these. So that's something, a follow-up for myself, like why is object create constant? It probably has to do with how Ruby allocates heap slots and whatnot, but I'm not quite sure. So you wonder, what does my program really do? What are the things called? And say I hadn't just showed you how to use perftools. This is another way you could look at it. You can hook method entry into Ruby code or into C extension code, and then get a log of everything that was ever called. So this is from the Laughable database. You can see person.2s is called, and person is called, and a bunch of faker stuff. So this is really fun to look at, like how Ruby Gems works. Ruby Gems does a whole bunch of stuff before your program even starts running, which is illuminating to look at. Ruby 1.9 and 2.0, am I done? All right, so I'll fly through this. It generates bytecodes. The bytecodes look like assembly. You can disassemble it with this Keith Richards pro tip. That's what a simple require looks like, pretty easy. That's what calling a block, and there's an inline cache that you might have heard about. This is what simple arithmetic looks like. Put object, call add. This is what add looks like, system calls, that's less interesting. dtrace, more Rolling Stones. Oh, there's a weird thing. System calls, yeah. Okay, and this is the C code for that plus operation, it takes some stuff. Here is the actual native C code. Right here is where the processor adds two numbers. This is a fall-through case. There's in this code, there's a whole bunch of type checking that looks for fixed nums and floats and arrays and active record base objects, or just regular old Ruby objects that it can't optimize. And this is where the one native instruction is. And this is why Ruby is slow. You've got all this stuff that's checking types for you and doing smart things. But here in the very middle, you call an actual assembly, an actual instruction that the processor can do a billion times a second. So it's a trade-off. And knowing about those trade-offs is useful and awesome. Now, bring it to me.
Thank you, Adam.
Thank you.